In the last few videos, I've described the back propagation algorithm, and if you try and train a simple network with it, it should work okay. But you might find that training more complex networks, for example ones with many inputs or many patterns, doesn't work so well. This is because back propagation has several issues which can cause it to fail. Two common ones are network paralysis and local minima. Let's have a look at those and see what they mean. Network paralysis happens if some of the weights move towards large values. This tends to slow down training and can bring it to a standstill. It and several other similar issues can be avoided quite often by using a parameter called the learning rate. We can add the learning rate parameter into our weight changes as shown by the equation on the screen. The learning rate is just a constant value with which we can speed up or slow down the rate at which a network learns. Making it large, greater than 1, speeds up learning but makes the network less stable. Making it small, for example 0.1, slows down the learning process but tends to make the network more stable and less susceptible to issues like paralysis. It can also make the network learn the patterns more thoroughly. Although network paralysis and similar issues may be a problem at times, possibly the most common problem with backpropagation training is the issue of local minima. The idea behind backpropagation training is that we change the weights in order to get the lowest possible error value. We can see what this means if we plot how the errors change as we vary a single weight in the network. This is shown by the plot on the screen. Although I haven't explained this in previous videos, the backpropagation algorithm works by always changing the weight so that the error decreases. This is an idea you may be familiar with if you've studied mathematics, as linear regression or similar algorithms. The idea of this is shown on the screen, and because of this, backpropagation is often called a gradient descent algorithm. However, there are of course many weights in a network, and they all interact with each other in complex ways. So the graph is often more complex than the one that I've shown above, with hills and valleys as shown in the graph on the screen now. Perhaps you can see the issue. Because the algorithm can only move the weights in the direction of a decreasing or downhill error, there is no way out of a valley. Such a valley is called a local minima, as we have to go uphill to get out of it, and so we get stuck. We can often see problems like local minima in the error profile of a network training as shown on the screen. Although having said this, we do have to be careful to wait long enough to ensure that the system really is stuck, as profiles like the one shown on the screen now are fairly common. So let's look at some methods of getting over these problems. The first method is simply to start again with a new set of weights. Obviously, being careful to seed the random number generator in your programming language so the weights really are new. This method is really the only way to deal with some of the problems of neural networks like network paralysis. Doing this is often enough to get the network working, but it is inefficient and time-consuming. A second method is to shake up the weights by adding a small random number to them if a network gets stuck, i.e. if the error is not decreasing anymore. You may have to do this several times though before the solution escapes from a local minima. The final and most common way is to add a term into the equations for training a network called momentum. This is added to the weight change equation as shown on the screen. In this equation, delta W is the weight change used for this weight in the previous iteration or cycle. Alpha is a constant between 0 and 1. What is happening here is this. The weight has been moving in a particular direction by a certain amount given by delta W, and we keep it moving in this direction by alpha delta W in the current iteration, so that even if the current change is close to 0, as it would be if we got stuck in a local minima, we keep going for a while in the direction which we were, which is hopefully long enough for the solution to escape. As you've seen, not all of these solutions work for every problem. So there's sometimes quite a lot of messing around to do in order to find a solution and get the network working. This is one reason why getting networks to work well is sometimes viewed as more of an art than a science. Also, what we just discussed assumes that there is a problem with the network training and not more general with the network configuration itself. For example, it could simply be that the network's too small and that's why it's not training. Size also has other impacts on network performance, as we'll discuss later. But for the moment, just note that if a network is very large, much larger than is actually required, this can lead to more local minima and other similar problems.